Okay, so now we are going to look at what is meant by stress components and stress matrix. The key here is that there is a notation that you have to understand. Okay, so this is our key math emoji if you want. If you understand and if you're able to interpret the notation, then everything else will become a lot simpler. Okay, so the stress components and stress matrix are an important idea. Okay, the same problem as before. Force is 100 newtons acting at 30 degrees to the y-axis. We now have to describe the stress components. So our force was 50I plus 86.6 J. Ty was 5I plus 8.66 J megapascals. Okay, what it is that there are two components to Ty, and that's what we want to talk about. This force intensity vector has two components. Like force vector has two components, force intensity vector has two components. And these two components, one is along the x-axis, the magnitude is 5 MPa. The other one is along the y-axis and the magnitude is 8.66 MPa. Okay, we are going to write this as Tyx equal to 5 MPa, Tyy equal to 8.66 MPa. So this is the emoji, this Tyx, Tyy. You have to understand what they mean. So the red items, the first index refers to which normal? That is what was there already. Can you see this Ty? That shows up as the first index. Then the second index represents the components. Direction of the force. X direction, Y direction. So this is our notation. Okay. This is very important to understand because everything else will be built off of this. Okay, once you understand this particular emoji, this Tyx, Tij, whatever it is, everything else will be simple. The first component always refers to a surface through its normal. So it will tell you which direction the surface is perpendicular to. In this case, the first index is Y, so it says the surface is perpendicular to the Y direction. The second tells you which direction is that particular component pointing. So the second index is X, and so the 5 MPa force is pointing in the X direction. For the 8.66 MPa force, the second index is Y, so the force intensity is in the Y direction. That's how you think about it, okay? So this has to be, again, this is critical for you to be able to follow whatever else is there in this entire FEA. If you don't understand this, you cannot use FEA properly. Okay. So the main idea is that the stress value at a particular point. So now we are talking about stress components. So remember the components of the force intensity vector is also called the stress components. So they depend upon two factors, the surface on which they act and the force per unit area. This is because the force intensity vector is a vector, so it has components. Okay. And we already mentioned these things are called stress components or casually stresses. So be very careful about this. So I always refer to stress components to mean like force components. They are numbers. When we talk about force intensity, it's a vector. So you have to be careful about which one we are referring to. Okay. Stress components at a given point are subscripted based on two criteria. First one is you can think of them as having 2 degrees of freedom. First one is the surface on which they act. This is described by the surface normal. Can you see different surfaces will have different surface normals? The second one is the direction of the force component per unit area. It could be up like this. It could be sideways this way. It could be some other direction. You're with me. So the combination of these two things is what we have to represent. That is how they are represented. Now we come to the most important item. This is called Koshi's theorem. And this allows us to find the force intensity on any surface. It says any plane. That's my typo. It should be any plane on any surface. So what I have here, you can see that there's a point, and there are 3 axes that are assigned X, Y, Z. We are going to look at 3 different surfaces. So Koshi's theorem says that if you know the force intensity at any point on 3 coordinate planes, XY, YZ, and XZ planes, then the stress intensity on any other surface is just a weighted average of these 3 force intensities. The weights are the components of the normal to the surface. It sounds kind of abstract, so let us make it a little bit more concrete. And then when we do a workout problem, you will see the exact concrete version of this, okay? So let's make it a little bit more concrete. So for this particular problem, the particular case, the traction intensity on the YZ plane is called Tx. And you're wondering, why isn't it called Tyz? Because please remember that the YZ plane is normal to the x-axis. So it has to be the force intensity or traction vector on that will have x as a subscript. Okay. Similarly, the XZ plane normal to y is Ty. That's the stress intensity on that one, force intensity on that one, and the floor, which is the XY plane, normal is Z, so it's called Tz. Okay, so these three, let us say we know these three. Now, suppose I have some other plane like that. The normal is Nx, Ny, Nz. We want to know what is the T of N here, the traction on this surface. You would think, okay, how am I going to do this? All I know is all this force intensity. It turns out that Koshi has a nice solution to it. It's extremely easy. You just do a weighted average. Nx times Tx plus Ny times Cy plus Nz times Tz. That's it. It's as easy as that. And you can see, if that it makes sense, the more closer it is to whichever phase, the more it has to have. That's why it is weighted with Nx, Ny, and Nz. Okay. Now, this is not convenient. Before we go there, why is this a big deal? Because if I know the traction vectors on just the coordinate surfaces, then I know the traction on any surface. So because of Cauchy's lemma, the traction vectors on the coordinate surfaces are called the state of stress. Okay, we will write it as a matrix because then this Cauchy's result can be written by doing matrix multiplication. That is what we are going to do, but this is the idea. Okay, so why do we care about all of this? When we come to assigning, boundary forces and things like that, you have to worry about which way it is and all of that, and then we'll have to think about this very carefully. Okay, but please remember that the way to remember formulae, don't memorize the formula. Don't remember Nx Tx plus Ny Ty plus Nz Tz. Remember the word version of it. That is actually my a text message. It has been compressed. The full version of it is here. Cauchy's theorem, Cauchy's theorem, that is, if you know the stress intensity is the weighted average of these three stress intensities or force intensities. Okay, this weighted average is the most important thing, and once you know that, then it's easy. And the weights are the components of the normal. If you remember those two, you're done. Okay, now how exactly do we do this state of stress? Okay, the key thing to remember and memorize this, it's called face the force. So what it is that it always refers to the fact that our stress emoji, our notation for stress, the first subscript indicates the phase, the second subscript indicates the force. So I've shown you all the stresses and all the stress components on all the phases. So three components on each phase. Now, if you look at the first one, I have marked it. Phase normal is x, the force direction is x. That is called SXX. Okay, some people will use T, some people will use S, some people use sigma. So there are three possibilities. People can use capital T, people can use S, people can use sigma. You should just be comfortable with either of them. Okay, now let's look at the next one. Phase normal is still x, force direction is y. So that is called SXY. Can you see? Phase normal is x, force direction is y. Then phase normal x, force direction z. Okay, now you try the top one, tell me what these things mean, and you will see that how well it works. Okay, so pause it, try it out, and then come back and see if I have the same version. So phase normal y, force direction x is called SYX. Can you see? Face normal y, force direction x. Face normal y, force direction y is called SYY. Face normal z, force direction z is called SYZ. Face normal z, force direction x is called SZX. You get the picture, right? I hope you do. Face normal z, force direction y is called SZY. Face normal z, force direction z is called SZZ. This is our notation. Okay, this whole thing is packaged into a matrix. Generally speaking, if I see Sij, the first subscript represents face normal, the second subscript represents force direction. Okay, now this is written in a matrix version, and I'm not going to go into it, but because of balance of angular momentum, it turns out that the stresses have to be symmetric for the cases that we are looking at. So notice that I write SXX, SXY, SYXZ, SYX, blah, blah, blah. This matrix is called the stress matrix. The symbolic version of this is this cube. So you should be able to go back and forth because the symbolic version will tell you which direction things are. Now, one last point. Can you see these three things? The diagonal things are called the normal stresses because they're pushing or pulling. The off-diagonal terms are called the shear stresses because they are sliding. Okay, and if you look at any row or any column, that will represent what is the stress intensity or force intensity on that face. So actually what we have done is we have taken the force intensity, the Tx, Ty, Tz that we talked about last class, and we put it side by side and made it into a matrix. Can you see that? Or in this case, we put it layer by layer. It doesn't matter whether you stack it vertically or horizontally because it's symmetric. You'll get the same answer. So we stacked it to create the stress matrix. Okay. Now we can use Koshi's result in a very nice way so that we can compute things. So that is where we are headed next. Okay. So what we are going to do is, let us look at a particular example. So I've given the state of stress. Find the traction on the surface, which is at 45 degrees to the xy plane. The normal is cos 45, sin 45, 0. Can you see that plane? We want to find out what's the traction vector on that plane. Okay, so what do we have to do? It's actually quite easy. We take the stress matrix, multiply it with the normal direction, you'll get the traction vector. That's as simple as that. This is what Koshi said before. Remember that we did all of that by writing it in matrix version. It's easy to do. So in our case, let's write down the stress matrix. I want you to do it. Look at this picture and convert it into a stress matrix. This will be an exercise that I'll ask you to do in class. You should be very comfortable with it and get used to this. So let's do that. So there's our stress matrix. 30, 50, minus 25, 50, minus 20, 25, 20, minus 25, 25, 0. The way I do it is to write the traction vector on each of these things in one column. So for example, 30, 50, 25. Can you see 30, 50, minus 25 because it's going in the negative z direction. So 30, 50, minus 25. Then I go 50, minus 20, 25. Right? Then I go minus 25, 25, 0. So notice if I don't say anything, that the corresponding force is 0. Okay, then multiply it with the surface normal. The normal to the surface was given as cos 45, sin 45, 0, 0.707. Multiply this, do a matrix multiplication. You'll get Tnx is 56.6, Tny is 49.5. All this in megapascals. Tnz is 0. Okay, it should be Tny and not Tby. Okay, this is how we compute stress. This is how we represent stress, and this is how we compute the traction on any surface. This is very, very important because this is how we know how to specify things on the boundary. Okay, last item. It's not that the stress will always be constant. It will be distributed in some way. And the stress matrix can be thought of as a nice way to package the force intensity vector. This is what will come out as output from your finite element package. It will give you this stress matrix as a function of location on each node. And this, you have to understand what that means. So it will be 6 functions in vector form. So it will give you this matrix. Txx as a function of xyz, tyy as a function of xyz, txz as a function of xyz, and so on. Or it will give it to you in a column vector. Txx, txyy, it says tyt, it should be tyy, and tzz, txy, txz, tyz. 6 vectors at 6 numbers at every node, or actually at every Gauss point. And we'll talk about that, what this Gauss point means at a later point, but this is what you will get. Okay. This is what it plots when you ask it to plot. This is the kind of result you should get. So you should understand what this means. So I'll give you a particular example. You all know about pure bending. You can see what these forces look like. I'll show you what this Txx, Txy, Tyz looks like. Txx is minus 3y. I just made up some number, but you can see that the phase is the x direction, force is either positive or negative x, and it is linearly varying with y. So that's why it's minus 3y. All the other tractions are 0. This is what we show by little arrows. This is what this means. So the arrows represent force intensity or traction vector on that face. Just the packaging is in the form of a matrix. That makes sense to you? This is how stress field or stress matrix at each point is represented. We are now going to talk about how to specify force distributions, and that's our next item. Thank you very much.